Hey, pre-calculus friends, here we are in chapter 4. We're looking at the rational root theorem. Our vocabulary today consists of three concepts: the rational root theorem, which is the title of our section, integral root theorem, which was really based off the rational root theorem, and Descartes' rule of signs. All of these are so much better to talk about in an example, but I will give you kind of a slight overview of each. So the rational root theorem says, hey, if you have any old generic polynomial equation, sometimes it's hard to understand with all these subscripts and everything. They're trying to make it so generic that we can understand that this could be any number. What I'm going to do is just write this generic fourth degree polynomial. The rational root theorem states that if you have this any polynomial and you want to figure out if it has a rational root, what you're going to do is this: you're going to find all the factors of the constant term, and we will call that the set of P. And then we're going to find all the factors of the lead coefficient, and we're going to call that set Q. And what we're going to do, maybe not capital Q, but we'll deal. What we're going to do is once we find all of those factors and all of these factors, the rational root will be any possible P over Q. If there is a rational root, if I take all the factors of this, plus or minus the factors of E, and all plus or minus the factors of A, and I set them up as a bunch of ratios, this group will be the only possible roots that could be rational for a polynomial equation of this form, all right? So that's pretty powerful. And then what's more powerful is if you notice that the Q terms are down here, the integral root theorem, if the root is an integer, you know that the denominator would have to be 1, right? If you had a rational root and the root was an integer, it would have to be 1. So the denominator would have to be 1. Therefore, the power, the heavy hitter here is P. Where did P come from? P is a factor of E. So what is that saying? If you have an integer root or an integral root for a particular polynomial, it will have to be some factor of E. And that's kind of neat if you think about it. And that's basically what's being said down here if you go through the information in the text. Finally, Descartes' rule of sign is a bit involved, and it's a bit slightly, I don't know, passe in a way, because it's not something that we think about, and I think this will be better saved for an example. Basically, it's a way of counting the possible number of positive roots and the possible number of negative roots depending on sign changes, and you'll see me do an example for you in just a moment. So let's start with this example 1. We're going to list the possible rational roots of this particular polynomial equation. Then we're going to determine the rational roots, determine which ones work. So remember, we're going to take the constant term and we're going to factor the constant term, and that's going to be our list of p's, okay? So, and I think lowercase p and lowercase q is how I should write that. So our list of p's are going to be plus or minus 2 and plus or minus 1. Those are the only factors of negative 2, or of that 2 there. And then we're going to do the same thing over here with the 6, and we're going to, or the lead coefficient, that's going to be our list of q's. And so the q values are going to be plus or minus 6, plus or minus 3, plus or minus 2, and plus or minus 1. And so now we need to find the set of all p over q. Now, this set of values will be the values that we will test to see if we have a rational root. And so now I'm just going to go through and see what I can do. So I'm going to put all p's over q. So I need to put the 2 over the 6, the 2 over the 3, the 2 over the 2, and the 2 over the 1. So that's going to give me plus or minus 2, that's 2 over 1, and plus or minus 2 6, which reduces to 1/3. And that's plus or minus 2/3. That's the 2 over the 3. And then plus or minus 2 over 2, which is 1. And then plus or minus 2 we already have. So we've got everything we could from this one relationship, right? We've got all the possible situations going on. The next thing we're going to do, looking where these commas go, the next thing we're going to do is take the 1 and put that p value over all of the q values. And so when I do that, you see I already got 1 over 1, that's happening. 1 over 2, that's not here, so I've got to make sure and add that as a possibility. 1 over 3 already there, so I'm not going to rewrite that, and 1 over 6, which is not there. So now I have every possible combination of P over Q. Now it's for me to try out which one is going to work. So if I had to do this by hand, which sometimes you might be called to do in a class, then what you would do is I would probably rock out with a little bit of synthetic division. You notice that this is in descending order already. And now what I'm going to do is take a look at some synthetic division and try. I'm probably going to, honestly, this is a third degree. All I need to get is one that works. One of these somewhere works. I want to try whole numbers so I can rule those out. If I can get a number that works, then all I need to do is reduce this to a quadratic. I can factor that and I'm good to go. So if you were here with me, students, I would ask you, what should we try? But since you're not, I'm just going to try 2. I have no idea what's working. I did not look at the answer, so I'm going to try 2 and see what we get. So I tried 2 and it did not work. So I'm going to now try -2. And I know I'm doing this fast. I'm not doing it with you, but you can just enjoy me doing the work for you. So I'm going to try -2 and let's see what happens. And so when I tried -2, it worked out nicely. Then I get this cool depressed equation. So worked out nicely because I have 0 as a remainder. So I know that that is a factor. So I know that x plus 2 is a factor of this particular polynomial. So now I've got the depressed equation, which is 6x squared minus 1x minus 1. And now I got to figure out how to factor this guy. So what I'm thinking here is that I've got two pairs of values that when I multiply them together in this way, the double V's is what I call it, is that I should get -1. So now I just got to put numbers around. So since I have a -1 in the middle, I'm feeling like 3 and 2 would be a good way to factor that 6. And then 1, there's only one way to factor 1, that's 1 and 1. And now it just depends on what I want to be negative and what I want to be positive. When I make this negative, this becomes a -3x. When I make this positive, it becomes a positive 2x. And I think we get exactly what we're looking for in the middle, which is that -1x when I add those together. So I'm feeling confident about my factoring. And now I've got all my roots. So how do I get my roots from factoring? Well, I got to make them all 0 and see what it is. So we remember we got -2 as a root. And over here, if I set this equal to 0, we'll get a positive 1/2. And if I set this equal to 0, we'll get a -1/3. So you can see all of these rational roots were predicted by our rational root theorem, and they were right there. So with this example, we're going to find the roots of this function, of this equation rather. And so to do so, I think we should probably start off with the rational root theorem. This doesn't look like a factor by grouping situation because I can see clearly that when I factor x squared out of here, I'm not going to get the same thing as if I tried to factor anything out of here, which doesn't seem to be anything that I can factor out of this pair. So what I'll do is I will rational root theorem. All the factors of the lead coefficient, all the factors of the constant coefficient, of the constant term. So that's plus or minus 5 and plus or minus 1. So those are the factors. Those are my P values. And my Q values are going to be simply just plus or minus 1. And so with that, all my P over Q values that I have will be as follows. Basically, it's just going to be plus or minus 5 or plus or minus 1, because if I put it over 1, it's just going to be what it is. And so now this is what I'm trying out. I think synthetic division is still the best bet for determining whether something is a root. And so at least now we only have 4 different choices to choose from. And since I said the number 5, I'm going to try 5. Drop my 1 and let's get started. So I've got my 5 here, 13. 5 times 13 is going to be what's that, 65, and this doesn't look like it's boding well at all. 16 plus 65 is a pretty large number. When I multiply that by 5, it's not getting canceled out, so I'm stopping this train of thought, and I'm saying that's not going to go, and I'm going to try -5 just because, and after that we'll try 1 and we'll see what we get. Okay, so try that -5, bring the 1 down, -5, we get 3, that times that gives me a -15. Okay, hello, 1, -5, yes. So here we are. We know that -5 is a root. Therefore, x plus 5 is a factor. Though they didn't ask us to factor, I just like thinking about it that way. Then I'm going to write down this depressed equation. X squared plus 3x plus 1. Factoring Does not look like it's going to happen. I can't think of any number that I'd multiply with 1 and 1 to get 3. You know what I mean? If we were to try to factor this out, doesn't look like anything's going to work. And so when you have a situation like this, what you're going to have to do is the quadratic formula, which we're good at. So we know that A is equal to 1. So I'm setting this equal to 0. Remember, I'm trying to figure out what the next zeros are. A is equal to 1, B is equal to 3, and C is equal to 1. And therefore, I'm looking for x, and x is going to be opposite of b, plus or minus the square root of b squared minus 4ac, all of that over 2a. And now when plugging in everything, it should work out pretty nice. Negative 3 plus or minus the square root of 9 minus 4 times 1 times 1. All of that over 2. And so with that, we get negative 3 is equal to, or x is equal to plus or minus 9 minus 4, which is going to give us 5, the square root of 5, all of that over 2. So these numbers are not easy to write because they don't really simplify. So I'm going to leave our answer here. Here are two roots. Our roots are negative 3 plus square root of 5 over 2. Our other root is negative 3 minus the square root of 5 over 2. And our other root, of course, is negative 5. So that's where our three roots are. Okay, so example 3 is going to require us to investigate Descartes' rule of signs. We're going to find the possible, so what Descartes' rule of signs tells us is the possible number of positive real zeros and the possible number of negative real zeros. And so the test goes like this. You first start off with the function, and then what you take note of is the sign changes. So this is the test for positive roots, okay? So you just take the function as it is and you test to see how many sign changes there are. There's no sign change here. There's one here because this goes from positive to negative. There's another here. That's another sign change. Here's another sign change, and here's another sign change. So altogether we have 4 sign changes. So the number, what the rule tells us, I'm going to scooch back up here to the rule. What the rule tells us is that the number of positive real zeros of p of x is the same as the number of sign changes of the coefficients of the terms, or is less than this by an even number. Let's take that information and scooch back down. So that means the number of positive zeros would be either 4, 2, or 0. Because what I've done is I've subtracted from these numbers by 2. Does that make sense? And then the test for the negative roots is going to look like this. What we do is we plug in this negative x, and then you see what happens to the side. So watch this. When I plug this negative x and I plug it in and I raise it to the 5th power, it's going to give me a negative result, so it changes this coefficient sign. Whereas when I plug the negative x in and I raise it to the 4th power, that 4th power is going to kind of obliterate the negativity, and so it's still going to be a positive 3x. I continue on in the same way, plugging in the negative x and then simplifying the situation. Then, I think you probably guessed it, I'm going to check for sign changes. The sign does change here. That's 1. The sign does not change. It doesn't. Oh, let's get that to happen. It does not. Let's try it again. Does not change here or here or here. So we only have 1 sign change. So this tells me there's a possibility of 1 negative root and 4, 2, or 0 positive roots. And you know, sometimes there can be real and imaginary roots and all that stuff. We know that we can have as many as 5 roots. So maybe we've got 4 positive roots and 1 real root. Why is this helpful? And I kind of called it passe, but if you have to struggle through figuring out what the roots are, like we're about to do, because they said then determine the rational zeros. So that sounds like a call to the rational root theorem. So if we have to determine that, and I'm going to start with my P over Q situation already, if we have to determine that, then what we need to be able to do is determine how many positives we have and how many negatives we have. It'll help in our searching. So I know I need to have all the factors of 3 and all the factors of 2. I'm trying to do this quickly. So I have plus or minus 3 over 2, plus or minus 3, plus or minus, I think that's it, plus or minus 3 and plus or minus 3 over 2. And then I've got to do plus or minus 1/2 and plus or minus 1. And it's 1 over 1. So I think I've gotten all the possible p's, factors of 3, over factors of 2. And now I've got to try those in this polynomial. Try some division, some synthetic division. So I better get comfortable with doing a couple of these synthetic division situations. Let me see what we can do here. So I'm going to start off with, let's start off with 1. Let's make our lives easier. And so if I start off with a positive 1, I'm going to get 2, 5 here, and then another 5, negative 1 here, 5, 5, negative 3, and negative 3. Yay for me. And then so I have this guy, and instead of continuing down the path, and that's also another thing, instead of continuing down the path and doing it again, I'm not going to try a new one. I'm just going to continue with this depressed equation and see if I can get another value that will work. So here's what I want to do. Okay, so we got that 1 is a factor, and now we need to try some other values. And let's try negative 3. So if we do that, we're going to get our 2 down here, negative 6, negative 1, positive 3, positive 2, negative 6, negative 1, and positive 3. And there it is. And I won't lie, I looked at the answer, so I wouldn't have to be doing too many of these. And I know you don't get the opportunity to do that, but just wanted to show you that it works. So since we already have the negative 1, and Descartes' rule of sign told us that we only have 1, then we should only be looking for positive values, and so we can keep searching. So there's a whole lot going on, but I'm going to choose the numbers that I know work. So 1/2 is the next one. Let's see how that works out. So we've got 2, negative 1, 2, and negative 1. I'm just sliding this all down, and I bring down my 2. 1/2 times 1. 1/2 times 2 is 1. That gives me a 0. That times 0 times 1/2 is 0. Bring down my 2. 1/2 times 2 is 1, and I get 0. And so now my depressed equation is into a quadratic, and I don't feel like I need to try as hard anymore. So this gets to be 2x squared minus, plus 2. Let me try that again because this looks weird. Plus 2 equals 0. So this is the last factor. Let's think about what our factors are. So our factors, if we were to factor this thing, we know we've got x minus 1, x plus 3. In a technical way, I would say 2x, 2x minus 1 to get that 1/2 if you kind of think about it. And this last factor is 2x squared plus 2. And so I need to figure out what the zeros are, but you can kind of tell. If 2x squared plus 2 is equal to 0, then 2x squared is equal to negative 2x squared is equal to negative 1. X is equal to plus or minus I, which is the square root of negative 1, which means imaginary. So these aren't real. We don't need to think about them. The rational roots that we got are 1, 1/2, and negative 3. And you can see we have 2 positive roots, which we expected according to Descartes' rule of sign. Helpful, but I'd probably rather graph it personally myself. So with that in mind, I'm going to end the video. I'm not going to do the next example because I think you have enough information to successfully handle section 4.4. So if you have any questions, let me know. I look forward to talking to you soon. Take care.